The derivative is defined to be a function that you take the limit of this difference quotient. If this limit exists, we say the original function is differentiable. We interpreted things as the slope of a function or an instantaneous rate of change. So the next chapter of the course, we are going to take time to develop a bunch of rules for finding derivative formulas, leading to using those formulas to solve problems. So before we get into that, we're going to talk about some notation. Up to now, we've discussed this notation. So this is prime, or the Newton notation. Another notation that we are often going to use is what's called the operator or the Leibniz notation. An alternative way of writing that would be as follows. And in all cases, they mean the same thing. They are all referring to the limit of this particular difference quotient. This notation is going to get used quite often, and it's handy because it tells you what function that you're using and what variable are you differentiating with respect to. So what's important to remember here is that you've got dummy variables. This notation implies that these two letters need to match. So another way to think of it would just be an empty box here. Whatever goes there has to match there. Now, another thing that is tricky for students to understand is this notation, we pronounce it d by dx. This is what's called the derivative operation. This is analogous to a plus sign or a division symbol or a multiplication symbol. This says, I am going to do something to a function. So whatever you put into this gap, this notation means I am going to do the derivative operation to it. It's waiting for you to do something. This notation says, I have already done something to the function f of x. This represents the derivative function. To be very deliberate, when we write f prime of a, this stands for a value. It's the slope value at the point a. Sometimes we are going to write it as d by dx of f of x at the value x equals a, and sometimes we might write it like this as well. And in all cases, the best way for you to think about it is as follows. Number one, find the derivative function. Number two, plug in the number you're interested in. We would like to come up with formulas for the derivatives of common functions. These are the functions that you've seen in pre-calculus class, functions that we are going to use over and over and over again. So for example, we have talked about constant functions. You could interpret a constant function as a flat line, a horizontal line, and you could interpret the derivative as the slope. So when we say this notation right here, we say, what is the rate of change of a constant function? Or what is the rate of change of a function that never changes? Or even another way of thinking of it, what is the slope of a function that has a horizontal line? So you should be able to see this derivative is 0. There is no change in a function that never changes. Similarly, if we talked about the function x, a linear function, you could interpret it as slopes. This function has a constant slope. Its slope is 1. So we've found two derivative formulas, and these are always going to be true. Now, last class, in the video, we went through the exercise of figuring out the derivative formula for x squared, and it turned out to give us 2x. Now, interpreting it visually, it says if I were to take some point on the graph, so for instance at x equals 0, I should get a slope of 0. If I go to x equals 1, the formula should tell me that the slope is different. And if I go to another location, let's say x equals -2, the slope would be -4. What about general powers of x? If I wanted to figure out the derivative of any power of x, what would it be? So if I wanted to do it for x cubed or x to the 4, is there a way to do it? There is. I'm going to restrict myself to what are called natural numbers. So the fingers and toes, x to the 1, 2, 3, 4, 5, 6, those numbers. Rather than doing them all one at a time, we can talk about them all at once. If we want to figure out a derivative formula, we need to start from the definition of the derivative. For this particular function, the definition of the derivative would get us to here. Now, I've continually tried to tell you when faced with the strange limit, you should sneak a peek. For this derivative and any other derivative, you'll always see 0 over 0, so that means you can't use the limit laws naively, so you have to do some algebra. Now, the algebra here is complicated by the fact that you have some value of n that you don't know. It could be 3, it could be 4, it could be 17,000. And so the algebra that is needed here is not obvious, and was something that was developed a long time ago by Newton, what's called the binomial theorem. It's essentially a way for you to expand any power of x. And it turns out that you can come up with a nice little formula for an expansion like this. The pattern is that one of the variables starts with the full power of n and the other one starts with the power of 0. And as you go down the line, one of the powers decreases for one variable and the other power increases. So we'll get x to the n plus nx to the n minus 1 times h. This is just going to be some stuff with the letter h. The x power will drop by 1, the h power will increase by 1. All that stuff in the middle is not important for us to come up with a precise formula for. What's important is for us to realize that it has h's in it. With that, we can go ahead and plug in the variables in the expressions that we want. So it's going to look messy. All of this stuff here will get plugged into the derivative formula. And I'm just going to be lazy and say stuff. And from that, we will subtract x to the power of n. If this derivative is going to exist, we have to find the h over h that's producing 0. And if we're lucky, some things will cancel. The x to the power of n does cancel. So we'll end up with a limit of n x to the n minus 1 times h plus some stuff with h's. And this will go all the way down the line. And all of this will be divided by h. So what's really important here is that everything in this expression contains an h. So if I factor it out, everything in there contains a power of h that is being multiplied by some other stuff. When I get to this expression, I will have something like this. A term that doesn't contain any h's, so the limit will think that this is a constant, and then I'll have some stuff with powers of h. So it will turn out that the limit laws can now apply, and I will be left with a limit of something that's treated as a constant plus the limit of some stuff that has h's. The point of the story is that this is going to go to 0, and this will end up being whatever that constant represents. So what we have found is that the derivative of x to the power of n has a very simple little formula. This is what's called the power law or the power rule. This is the easiest point of this course. Enjoy, bask in the easiness. Now, even though I've proven it only for natural powers of x, it turns out it will hold for any number in the exponent. So n can be any real number. And we're just going to state that and assume that right off the bat so that when we're faced with things like this, the idea is that we can interpret this as a negative and then use the power rule. It's really important to make sure we get our negative straight. This allows us to deal with things that seem really complicated. Oh, x to the power of 1001. Well, that actually turns out to be pretty straightforward. And it also allows us to deal with things like roots. So if I had the fifth root of x to the power of 4, because I can write this as a fraction, I am able to use the power rule. Now, what's going to be important is being able to deal with fractions. So just like up here, if I wanted to, I could write this in terms of a positive power. I could write this as 1 over the fifth root of x.